Today, we look at the lines between the parts of a computer and follow one keystroke across the whole machine. You do not need any background. How the parts talk to each other. Every picture of a computer has lines between the boxes. Yours has them, ours has them, and almost nobody explains what they are. First question: what is one of those lines actually made of? A line on a drawing is easy. A real one has to be something. Second question: why are some of them drawn fatter than others? That is not decoration. It means something specific. And the third one is the whole series in a single question. What happens from end to end when you press a key? One last piece, and then we have the whole machine. This is the picture we have been building all along. Today the subject is not the boxes. It is what runs between them. This one carries data between the processor and main memory. This one goes out to the graphics card. Notice how much heavier it is drawn. And this one to the drive is thinner. These weights are not decoration. They are telling you something true about the links, and now we can say what. Start with the smallest thing there is. This is one lane, a pair of wires carrying bits one after another in single file. One lane is plenty for something like a network card. And a quick warning: this is how one family of links is built, the ones marked PCIe on the picture. Your keyboard's cable is a different kind of link with its own rules. Not everything on that board is made of these. Now 4 lanes, laid side by side and used as one link. 4 separate single files, all running at the same time. That is the sort of link a drive gets. More to carry than a keyboard, but not the most in the machine. And 16 lanes. Same idea again, just more of them, and this is the widest link on an ordinary board. It goes to the graphics card, which needs to be fed more data than anything else in the machine. That is why that arrow was drawn so heavy. Now the part that matters. Inside any one of these links, every lane runs at the same rate. So the 16-lane link is not 16 faster wires. It is 16 wires of the same speed, side by side. Which does make it quicker to send a big pile of data, because the bits get spread across all 16 and the whole pile finishes sooner. That part is real. But here is what width cannot do. It cannot make the thing at the other end answer any quicker. A wider road does not make the shop serve you faster. That is why main memory still takes about 100 nanoseconds. Most of that is the memory chips themselves finding the row you asked for, and no amount of extra width removes it. More lanes bring back more at once. They do not make the answer come sooner. This is the whole machine, and almost every part of it is something we have opened up. Let us press one key, the letter A, and follow that all the way to the screen. You press A, the keyboard writes down which key that was and waits. A chip on the board asks it, hundreds of times a second, whether anything has happened. This time the answer is yes, and the letter A goes up the USB cable. It arrives at the input and output hub, the part of the board that collects the slower devices together. And this is the moment to say what all these links really are. Wires only carry electrical signals going up and down. For that to become a message, both ends have to agree on rules, where a message starts and stops, whether it is a question or an answer, who it is for, and how you check it arrived intact. Those agreed rules are called a protocol, and every link on this board has one. That is what the lines are really carrying. So the hub packs the A into a message and sends it along its link to the processor. Now, how does a core even know to look? It does not sit there checking. The hub raises a signal that interrupts whatever the core was doing, which is exactly what that is called. The core drops its work, reads the A, and runs the program that deals with it. Most of what that core needs is already close by in the caches. The biggest of them is L3, shared by every core, and it has been holding this work for a while. What is not close is out in main memory, and fetching it costs 100 nanoseconds that the core spends waiting. The processor does not draw the letter itself. It works out what needs drawing and sends instructions for it, plus the shape of the A, across the widest link on the board. Now the second processor takes over, the GPU, and does what it is shaped for. Every dot on the screen gets a color, and thousands of small workers do it at the same moment. The finished picture is held in the card's own memory, labeled VRAM here, which just means the memory belonging to the video card. And it is sent out to the monitor, 60 times a second, whether anything changed or not. And your A is on the screen. One thing you might notice, the drive was never involved. It did its job earlier when the program was loaded into memory. Not every part takes part in every moment. One honest note to finish on. All of that happens far faster than it takes to say, and most of that time is not spent computing. It is spent waiting for something to arrive. That has been the quiet thread through all 6 videos. 6 videos, 1 machine, all of it in 5 lines. A processor that fetches an instruction, works out what it means, does it, and writes the answer back. Billions of times a second. Memory in levels because close is small and far is slow, and nothing gets you both. A drive that remembers when the power is off, and is slow and awkward to write to precisely because of what makes it remember. A second processor, shaped completely differently, for doing one simple thing to an enormous pile of data at once. And links between them all, wires, plus the agreed rules that turn signals into messages, carrying everything from one part to the next. Look back at that one keystroke and you can see all 5 jobs from the very first video doing their turn. Talk to the world, compute, remember now, compute again, a different way, talk to the world again. Remember later was the one part that sat it out because it had already done its work. And that is the thing worth taking away. No single part makes that journey. Each one follows its own small rules, and the links are what turn a box of separate parts into one machine. We started with boxes and unexplained lines. Every box now has a job, and every line carries a conversation. Thank you for watching.